Good morning everyone. Welcome back to next lecture. Today we will continue our discussion regarding the input-output analysis. See, in the last lecture, we discussed what the input-output analysis actually means, what are its various assumptions, input-output table or input coefficients and general formula for finding the output of each industry. See, the input-output analysis is an economic method which is used to study the interrelationship and interdependencies between different sectors of an economy. And it actually examines how changes in the one sector affect the others and the overall economy. So here, the mutual relationship or mutual interdependencies which actually leads to the equilibrium between the supply and demand in an economy. So it means that the total output must so much that which is consistent with all input requirements and the final demand so that there will not be any type of bottlenecks. We have derived the formula by comprising the technical coefficient matrix, output vector and final demand vector. Today we will discuss what are the Hawkins-Simon conditions and then go for solving the problems related to the two industry or two sector models. See, what are the Hawkins-Simon condition? See, there is a possibility that in the last lecture we are given the input-output table, and in that particular input-output table may provide the output which expressed by a negative numbers. See what happen if the given values are negative number. If it is happen, then it means if the input requirement from the one sector to produce the output of the another sector are greater than the output of the producing sector itself. That means the negative output of the one sector is used as an input for the other sector. See, it is such a situation will be, it is unrealistic and economically it is not viable. So here D. Hawkins and H. A. Simon introduced two conditions to overcome these problems. So these conditions are commonly known as it is Hawkins-Simon conditions, and this condition is actually describe a necessary condition for the existence of a positive solution for the Leontief input-output model. See, these two conditions are, the first one is the determinant of a matrix, that is identity matrix minus the coefficient matrix, that is I minus A, must be always positive. That is, the determinant value must be greater than 0. So that means it should be a non-singular matrix. So the determinant condition ensures that the matrix is a non-singular, which indicates that it have a unique inverse, because in order to find out the output of the each sector, we have to find the inverse. So for that, our determinant value must be positive, or it means it is non-singular, and thus ensuring the existence of a positive solution to the Leontief input-output analysis. Then the second one, it is that diagonal elements of a matrix, that is identity matrix minus A, that should all be positive, which means that the diagonal elements of this given matrix must be greater than 0. So the diagonal elements here, it will be 1 minus A11, n minus A22, 1 minus ANN. So these are the diagonal elements, it must be positive. And this condition is actually ensure that each sector produce more than its needs for its own production, indicating there will be a net surplus in the output. If any diagonal elements is 0 or it is negative, then the sector cannot produce enough output to satisfy even its output and the input requirements of the another sectors, so which would be economically infeasible. So these conditions actually, that means Hawkins-Simon conditions are actually ensure that all the sectors can produce a positive output given specified input-output relationship and the final demand vector. Now, we are going to consider one example. In an economy, there are two industries are there, that is X and Y. The following table that is giving the demand and supply in the crores of rupees. So here we have a producing sectors, that is X and Y. Consumption sector is also X and Y. This is actually showing the intermediate demand, or it is inter-industry demand. And the final demand is also given, that is 15 and 10, and the gross output is equal to 50 and 60. Now here, what we want to find out? We want to find out the coefficient matrix. First we want to find out the coefficient matrix. Then we want to determine the output when the final demand, that is 15 and 10, which changes to 35 instead of 15 and 42 instead of 10. Then what will be the level of output which is required? So we are going to find the coefficient matrix first. See here, we are going to construct the technology coefficient matrix here. So for constructing that, we have to find the proportion, that is A11, A12, A21 and A22, because we have a 2 by 2 model here. That means we have only two producing sector, that is X and Y. So A11, that is here, it is 10 divided by the gross output, that is 50. That we can write it is 1 by 5. A12, which is equal to 25 divided by 60. It will be like this: 10 divided by 50, 25 divided by 60. Then we have A21, that is 20 divided by 50. And we have finally A22, that is 30 divided by 60. So by solving this, that is we have 1 by 5, 5 by 12, 2 by 5 and 1 by 2. See, these are the various elements in the coefficient matrix. So we are going to write the coefficient matrix in terms of A. The matrix A is equal to coefficient matrix, which is A11, which is 1 by 5, A12, which is 5 by 12, A21, which is 2 by 5 and A22, which is 1 by 2. So this is the coefficient matrix. See, after finding the coefficient matrix, we want to find the output of the each industries. So for that, see, first we have to find out the I minus A, or it is identity matrix minus the coefficient matrix. So we know the coefficient matrix is, it is 2 by 2 matrix, and the identity matrix having the, the same order, that is 2 by 2 order, that is 1 0 0 1. This is the identity matrix minus A, that is the coefficient matrix, that is 1 by 5, 5 by 12, 2 by 5 and 1 by 2. Now if you go for subtracting these matrices, then it will become, see, 1 minus 1 by 5, which is equal to 4 by 5, 0 minus 5 by 12, which is equal to minus 5 by 12, 0 minus 2 by 5, which is equal to minus 2 by 5, 1 minus 1 by 2, which is equal to 1 by 2. So we have this particular matrix, that is identity matrix minus the coefficient matrix I minus A. Now, this is the, see here, all the diagonal elements, that is 4 by 5, 1 by 2, all are the positive, which is one of the requirement for the Hawkins-Simon condition. So the first condition is satisfied, that is all the diagonal elements are positive. Now we are going to find the determinant of a given matrix. So we are going to find the determinant of this particular matrix, that is 4 by 5, minus 5 by 12, minus 2 by 5, 1 by 2. So if you go for finding the determinant value, then it is 4 by 5 into 1 by 2 minus 5 by 12 into minus 2 by 5. So I am writing here, and if you go for multiplying 4 by 5 into 1 by 2, which is equal to 4 by 10 minus, see, minus 5 by 12 into minus 2 by 5, which is equal to 10 by 60. So if you take the common denominator, that is equal to 60, by multiplying 6, the first element, by 6, then it is 6 into 4 minus 10, which is equal to, which is 24 minus 6 into 4, which is equal to 24 minus 10 divided by 60. So if you go for simplifying it, then 14 divided by 60. So this is, we can simplify it as 7 divided by 30, which is equal to greater than 0. So the determinant value is equal to 7 divided by 30. So it is greater than 0. So it is a non-singular matrix. So it is not equal to 0. So the main diagonal elements matrix are, of course, we are already said that it was positive, and the determinant value is also positive. We can say that the Hawkins-Simon conditions, that is both conditions are satisfied. Therefore, the problem have a particular solution. Now after finding the determinant value, we are going to find the inverse of the given matrix. For finding the inverse of a given matrix, see, first we are going to find the inverse of given matrix by using this particular matrix. First we are going to find the minors of this matrix. So minor for the 4 by 5, which is equal to, by crossing the first column and the first row, what is remaining? It is 1 by 2. Minor second, that is minor for minus 5 by 12, which is equal to crossing the first row and the second column, what is remaining? It is minus 2 by 5. The third, that is third minor M21, which is equal to, it is, what is remaining here? It is minus 5 by 12, and the fourth minor, which is equal to 4 by 5. So after finding the minor, you know, it is, we want to find the cofactors. See, I am writing the minors separately here so that cofactor can be easily calculated. The cofactor 1, that is C11, which is equal to minus 1 raised to the power 1 plus 1 into the first minor, which is equal to 1 by 2. So minus 1 square, which is equal to 1 into 1 by 2, which is equal to 1 by 2. The second cofactor, that is C12, which is equal to minus 1 raised to the power 1 plus 2. So it is minus 1 cube, which is equal to minus 1 into the second minor, that is minus 2 by 5. So minus minus will become plus, so it will be 2 by 5. The third cofactor, that is C21, minus 1 raised to the power 2 plus 1. So it is minus 1 cube, which is equal to minus 1 into the third minus 5 by 12. So minus 1 minus will become, it is plus 5 by 12. Then we have the fourth cofactor, that is C22, which is equal to minus 1 raised to the power 2 plus 2 into the fourth minor, which is equal to 4 by 5. So it is 1 into 4 by 5, which is equal to 4 by 5. So I am writing these cofactors separately here. The four cofactors are written here. Now after finding the cofactors, you know, we want to find out the cofactor matrix. See, cofactor matrix, what is the cofactor matrix? We are going to replace the each and every element in the original matrix by using the cofactor elements. So here the cofactor matrix are 1 by 2, 2 by 5, 5 by 12 and 4 by 5. So this is the cofactor matrix. After finding the cofactor matrix, we will go for finding the adjoint of a given matrix. So it will be, see, if you go for taking the transpose of cofactor matrix, you will get the adjoint. So we are going to interchange columns, rows into columns. So it will become, see, 1 by 2, 2 by 5, 5 by 12 and 4 by 5. So this is the adjoint. See, after calculating the adjoint, you can directly go for calculating the inverse of matrix. See, the inverse of matrix is 1 by the determinant value into the adjoint of a matrix. So here 1 by the determinant value which we are already calculated, it is 7 by 30, which is not equal to 0. So it is a non-singular matrix. Of course, we will have an inverse, that is solution is exist. The inverse can be found. So we can go for substituting the determinant value and adjoint on the given equation or given formula so that you can find the inverse of given matrix. So the inverse of matrix, which is equal to 1 by 7 by 30, this is the determinant value, that is 7 by 30 into the adjoint, that is that adjoint value I am going to write here. By taking the reciprocal, that is, we can write it is 30 by 7 into the adjoint values are written here. And if you go for multiplying 30 by 7 into each and every element of the given adjoint, then it will be, see, by multiplying and simplifying, we can write it is 15 by 7, 25 divided by 14, 12 divided by 7 and 24 divided by 7. So this is the inverse of given matrix. So after finding the inverse, see, this is the inverse I am writing here. We want to determine the output when the demand changes to the 35 for commodity X or sector X and 42 for Y. So our final demand vector, or the constant matrix will become 35 and 42. So this is the D, that is the final demand vector, which will become, now as per the question, it is 35 and 42. Now we are going to multiply this constant matrix with the inverse. Of course, we have inverse. See, it is 2 by 2 matrix and it is 2 by 1 matrix. Of course, the matrix multiplication is possible. And if you go for multiply these two matrices, then it will produce a 2 by 1 matrix. So here, how we will going to multiply these two matrices? See, the first row will be multiplied with these elements and then the second row with the concerned column. Now it will become 15 divided by 7 into 35 plus 25 divided by 14 into 42. Similarly, the second row, that is 12 by 7 into 35 plus 24 by 7 into 42. I am writing here separately, and if you go for multiply and added accordingly, then it will be simplified as 150 and 204. So what actually this matrix, this result is showing? The output of the industry X should be 150 crores and Y should be, it is 204 crores as per the given problem. So now we have another example. We have a technology matrix is given and find the output of the each industry and determine the labor time which is required to produce the output as well. See here, the technology matrix or the coefficient matrix is already given. In the earlier example, the technology matrix is not given and we want to find out the technology matrix. But in this particular example, see, the technology matrix is given and we have two industry here. One is steel industry and another one is coal industry. So on the horizontal and the vertical level, we are taking the two industry, that is steel and coal. So we have a 2 by 2 model, that is 2 sector model or 2 industry model. And the final demand is also given, that is final demand vector, that is 50 and 100. So here first we are going to write the technology matrix separately. 0.4, 0.1, 0.7 and 0.6. These four elements will become the technology matrix. So I am writing here. So now I am going to write this particular matrix separately here. So here the matrix A is equal to 0.4, 0.1, 0.7 and 0.6. We have a 2 by 2 matrix and this is known as the coefficient matrix. And this particular matrix is given. Now we want to find out the technology matrix by subtracting from the identity matrix. So identity matrix with the similar order, that is 2 by 2, that is 1, 0, 0, 1 minus this particular coefficient matrix 0.4, 0.1, 0.7 and 0.6. So we are going to subtract this particular matrices. Then it will become 1 minus 0.4 which is equal to 0.6. 0 minus 0.1 which is minus 0.1, 0 minus 0.7 which is equal to minus 0.7 and 1 minus 6 which is equal to 0.4. So here see the diagonal elements are positive. So the first condition of this Hawkins-Simon condition are satisfied. Now after finding this particular matrix, we want to find the determinant value. See the determinant value here, we are going to multiply. See here we are going to find the determinant value of the given matrix. So here we are going to multiply 0.6 into 4 minus 0.1 into 0.7. So it is 0.6 into 0.4 which is equal to 0.24 minus 0.1 into 0.7 which is equal to, it is 0.07. So if you subtract this, then it will become 0.17. See this 0.17 which is nothing but it is the determinant value. See, after finding the determinant value, of course, this determinant value is positive. So, of course, it is a non-singular matrix. We can say that all our diagonal elements are positive and the determinant value is positive. We can say that the system is viable. That means Hawkins-Simon conditions are satisfied. We can find the solution by using the inverse method. See here, the matrix is given and first we want to find out the minor. See, the minus of 0.6. Here it is crossing the first column and the first row which is 0.4. Then second minor which is equal to, it is crossing the first row and the second column which is equal to minus 0.7. The third minor which is equal to crossing the first column and the second row which is equal to minus 0.1. Then the fourth minor which is equal to crossing the second column and the second row which is equal to 0.6. After finding the minor, I am writing the minor separately here. We want to find out the cofactors. So the cofactors here, C11, it is minus 1 raised to the power 1 plus 1 into the minor which is equal to 0.4. So 1 into 0.4 which is equal to 0.4. The second cofactor which is equal to minus 1 raised to the power 1 plus 2 into the minor second, that is minus 0.7. So minus minus will become plus, so it is 0.7. The third cofactor, that is C21, that is minus 1 raised to the power 2 plus 1 into the third minor which is equal to minus 0.1. So minus minus we have, it will become plus 0.1. Then the fourth cofactor which is equal to minus 1 raised to the power 2 plus 2. So it will become minus 1 raised to the power 4 into the fourth minor which is equal to 0.6. So it is 1 into 0.6 which is equal to 0.6. So after finding the cofactors, see, we are going to frame the cofactor matrix by replacing the original matrix by using cofactors. So here it will become 0.4, 0.7, 0.1 and 0.6. See, after finding the cofactor matrix, we are going for finding the adjoint of a given matrix. If you go for taking the transpose of given cofactor matrix, that means by changing the columns into rows, it will become, adjoint, that is transpose of cofactor matrix, which is equal to 0.4, 0.1, 0.7 and 0.6. See, after finding the adjoint, we can go for calculating the inverse of matrix. See here, inverse is equal to 1 by the determinant value in the adjoint. So here determinant value which we were already calculated, which is 0.17 into then the adjoint, that is 0.4, 0.1, 0.7 and 0.6. See, if you go for multiplying 1 by 0.17 into these elements, then it will become, see, along with that, we have a given the final demand vector which is equal to 50 and 100, which is given in the question. So we are going to multiply these things here. See, this is the inverse and we are multiplying the vector D, that is constant vector, that is final demand vector here. So if you go for simplifying it, then first I am multiplying this particular 2 by 2 matrix into 2 by 1 matrix. So it will become 0.4 into 50 plus 0.1 into 100, then 0.7 into 50 plus 0.6 into 100. So we will have a 2 by 1 matrix. We are going to multiply 1 by 0.17 into these particular elements. Then it will become 1 by 0.17 into, if you go for multiplying and simplify, it will become 30 and 95. If you go for multiplying these elements, then it will become 176.5 and 558.8. See what actually this is showing? It is the steel output is 176.5 tons and the coal output will be 558.8 ton. So we are writing here the steel output and the coal output, and we have a final question as well. We want to find out the total labor days required, and the total labors are given, especially in the steel, that is 5, and in the case of a coal it is 2. We are going to multiply the number of labor hours with the output of concerned industry, then we will get the total labor days required. So the total labor days is equal to, it is 5 labors into the output of the steel industry plus it is 2 into the output of the coal industry. So here 5 into the output of the steel industry, which is 176.5 plus 2 into the output of the coal industry, which is 558.8. If you go for simplifying it, then it is 882.5 plus 1117.6, and if you add these two terms, then it is equal to 2000.1. We can simply say that 2000 labor days are required for producing 176.5 tons of steels and 558 tons of coal. I hope you understood the concepts and how to calculate the output by using the matrix inversion method. So it is actually the input-output analysis is actually, it is an application of the inverse of matrix. So let me conclude here. Today we have discussed the Hawkins-Simon conditions and we solved the problems related to the two sector models. In order to find out the output of the each industry, we have used the inverse of matrix and then multiplied with the constant vector, that is final demand vector. I hope it is clear to you. In the next lecture, we will discuss a 3 industry model case, and we will see in the next lecture. Thank you.